All right, so let's begin. Lecture 9, Math 424. Are there any questions you have about homework problems or anything else that we've done so far? So I'm very happy to start doing problems.
Professor, can you do question 13 on page 328?
Let's take a look. So page 328, number 13, we have a homogeneous second order equation with the initial condition y equal 2, y equals -1 when x is equal to 1. So if we remember the basic form, or you really don't have to remember it because we have the book, but you have y double prime plus ay prime plus by equals 0. So this is a second order linear ordinary differential equations, homogeneous with constant coefficients. A is -4, b is -1. So d is a squared minus 4b is 16 plus 4 is 20. And k is the square root of d over 2. Square root of 20 is 2 root 5 over 2 is the square root of 5. So we're in the case d is greater than 0. So we have solutions u1 of x equals e to the kx, which is e to the root 5x. And u2 of x is e to the minus kx, which is e to the minus root 5x. And the general solution is y equals e to the minus ax over 2. So minus a is 4 over 2 is 2. So we get e to the 2x times some constant, c1 e to the root 5x plus c2 e to the minus root 5x. So this is the general solution to this second order equation. Okay. So any questions about how we got to this so far? So then we must choose the constants C1 and C2 to satisfy the initial condition. And that's not hard in principle. It may be a little bit hard in practice because we're not solving when x equals 0, which makes everything a lot easier. So let's see, this is y. And what is y prime? When we differentiate this, we get 2e to the 2x times y plus e to the 2x times what you get when you differentiate this, which is root 5 c1 e to the root 5x minus root 5 c2 e to the minus root 5x. All right, okay so far? So when you evaluate y at x equal 1, you get e squared c1 e to the root 5 plus c2 e to the minus root 5. And that is supposed to be equal to 2, because when x equals 1, y equals 2. So we have this linear equation. And what is y prime of 1? Well, when you plug in y prime of 1, you get 2e squared times y of 1 plus e to the 2, e squared, root 5 c1 e to the root 5, x is 1, minus root 5 c2 e to the minus root 5. And y prime of 1 is equal to negative 1. So let's see, what is this? This is 2e squared y1. Sorry. Yeah, this was really 2e to the 2x times y. Sorry, when you differentiate this, you get, by the product rule, 2e to the 2x times this, which is 2 times y, plus e to the 2x times the derivative of that. So so y prime of 1 is 2 y of 1 plus this, and y of 1 is equal to minus 1. Sorry, y of 1 is equal to 2. So this is 2 times 2 plus this. So just to rewrite this, I can factor out a root 5 e squared. So e squared root 5 times e to the root 5 c1 minus e to the minus root 5 c2 is minus 1 minus 4 is minus 5. Right? So what we have now is just a messy high school algebra problem. So from the first equation, for y1, we have e to the root 5 c1 plus e to the minus root 5 c2 equals 2 e to the minus 2. Right? So I just took this equation, brought the e squared to the other side. It's this equation in unknown c1 and c2. And this second equation, we have e to the root 5 c1 minus e to the minus root 5 c2 equals minus 5 over e squared root 5, which is minus root 5 e to the minus 2. And in the unlikely event that I haven't made any arithmetical mistakes, I doubt that, but if I add these two equations, I get 2 e to the root 5 c1 equals this plus this, 2 minus root 5 e to the minus 2. So c1 is 2 minus root 5 e to the minus 2 over 2 e to the root 5. So this is 2 minus root 5 over 2 e to the minus 2 plus root 5. Yep. So that's C1. And then you take the C1, you plug it into one or the other of these equations, you solve for C2, and after you do the high school algebra, you'll make a mistake or two, you'll do it again, you'll make another mistake, and eventually you'll clean up all your mistakes and get it right. So that seems to be a way to do it. Are there any questions about that? It's, you know, it's a second order homogeneous equation with constant coefficients. Theorem 8.7 on page 326 says how to find the general solution to the equation. That's how we got this. This is the general solution. And then you plug in the values when x equals 1 into y and y prime, and you get two linear equations and two unknowns. The unknowns are the constants C1 and C2, and you solve for them and you get your answer. And you know what the answer is because I emailed everybody and posted on the website the solutions to every problem in this chapter on ordinary differential equations. So you can check your work against the answers in the book. Sometimes the book is wrong, but not always. And so it's more likely if there's a conflict between you and the book that you made a mistake. But sometimes the book is wrong. Any other questions about homework problems?
Yes, hello.
Yeah, go ahead.
Yes, can you do from homework for number 5?
On page 333.
Right. Thank
Okay.
you.
Let's try. Hopefully it's not too hard. So this is page 333, number 5, which is y double prime minus 5y prime plus 4y equals x squared minus 2x plus 1. Okay. That's the problem?
Yes, of course.
Okay. So this is a second order equation with constant coefficients. And we don't need to use the whole general theory to solve this problem, because we know there's an easier way when the right-hand side is a polynomial. If the right-hand side is a polynomial and the differential equation involves the unknown function y, we only have to look for a quadratic equation, a polynomial of degree 2, that might be the solution. So suppose we let y1 be some polynomial of degree 2. I will use capital letters, ax squared plus bx plus c. So I want to find a, b, and c that satisfy this equation if I can. So the first derivative is 2ax plus b, and the second derivative is just 2a. So if I plug into this equation, I get y double prime, that's 2a, minus 5 times y1 prime, that's 2ax plus b, plus 4 times y1, which is ax squared plus bx plus c. I get this polynomial of degree 2. And when I collect the terms, let's see, let me just expand it. This is 2a minus 10ax minus 5b plus 4ax squared plus 4bx plus 4c. So when you do arithmetic, everybody makes mistakes, and I make a lot of mistakes. So you just need to watch what I'm doing, and if I make a mistake, tell me as soon as you see it. Let's see. This polynomial is 4ax squared. And then you have several terms that involve an x. You have 4bx minus 10a x. And then you have constant terms, 2a minus 5b plus 4c. So if I take a polynomial of degree 2, look at its first and second derivatives, and plug into this equation, this is what I get. And 2a minus 5b plus 4c is the constant term. 4b minus 10a is the linear term. And the coefficient of x squared is 4a. And this is supposed to be equal to the right-hand side, x squared minus 2a plus 1. So what that tells us, x squared minus 2x plus 1. So when you equate coefficients, first of all, 4a equals 1, so a has to be a fourth. The linear term minus 2 is equal to 4b minus 10a. But we know what a is. It's a fourth. So minus 2 is 4b minus 5 halves. So 4b is 5 halves minus 2, or a half. So b is an eighth. So we just found a and b, and what about c? Well, from the constant term, 1 equals 2a minus 5b plus 4c. So 1 is 2 times a. A is a fourth, so 2 times a fourth is a half, minus 5 times an eighth minus 5 eighths plus 4c. A half minus 5 eighths is minus an eighth. So 4c is 1 plus an eighth, which is 9 eighths. So c is 9 over 32. So we're done. A is a fourth. B is an eighth, and C is 9/32. So if you let y1 be equal to a fourth x squared plus an eighth x plus 9/32, that's a solution of the differential equation. And if you check, you plug in and check, you will see that it works. So we were successful, which is always nice.
So that method is called undetermined coefficients. I don't know the name.
No, that's not what it's called. But in any case, it doesn't matter what it's called. It doesn't need a name. You just do it. Right. The name's not important. What's important is that you can solve the problem. Okay. Any other homework problems or other problems I can try to solve?
I got confused with that. The last one is 11 from the same page. Page 333, exercise 11.
Okay.
Yeah, the last one. Thank you.
So let's see. So this is page 333, number 11, which is y double prime plus y prime minus 2y equals e to the x plus e to the 2x. Well, so we learned there's a special technique for these constant coefficient problems when the right-hand side is a polynomial or an exponential times a polynomial. And so let's just, so there are different ways to do it, but let's just say this is not a polynomial and it's not an exponential polynomial. So we have to use our general method for solving this kind of equation. So first we look at the homogeneous equation. So in this, if you think of y double prime plus y prime minus 2y is, y double prime plus ay prime plus by. So in this example, a is equal to 1 and b is equal to minus 2. So d, which is a squared minus 4b, is 1 minus let me just make sure I copy this down right. So a squared y double prime plus y prime minus 2y. So a is 1, b is minus 2. A squared minus 4b is 1 minus 4 times minus 2 is 1 plus 8 is 9, which is positive. And k, which is root d over 2, is root 9, which is 3 halves. So we're in the case when d is positive, and we have to, so the general solution looks Everything I said is correct. So we need to find solutions of the homogeneous equation. So the homogeneous equation is y double prime minus y prime minus 2y equals 0. And in that case, the general solution is y1 equals e to the ax over 2, e to the minus ax over 2, e to the minus x over 2 times c1, v1 of x is equal to e to the kx, e to the 3/2 x, v2 of x is e to the minus 3/2 x, c1 e to the 3/2 x, plus c2 e to the minus 3/2 x, which is equal to c1, when I multiply through, e to the x plus c2 e to the minus 2x. No. Actually, let me not solve the homogeneous equation and just follow the method in the book instead of doing it my way. So we need to know what v1 of x and v2 of x are. And v1 and v2 are solutions of the homogeneous equation. So v1 of x is, the general formula is e to the minus ax over 2, e to the kx, and v2 of x is e to the minus ax over 2, e to the minus kx. So a is equal to 1. So this is e to the minus x over 2, e to the 3x over 2, which is e to the x. And this is equal to e to the minus x over 2, e to the minus 3x over 2, which is e to the minus 2x. So e to the x and e to the minus 2x are the solutions of the v1 and v2, the solutions, the fundamental solutions of the homogeneous equation. All right, so that's the first step. So are there any questions of that before I go on? And then the general solution of the homogeneous equation will be linear combinations of these, but that's not what we're going to use right yet. Okay. Is that all right? Any questions? Okay. So then we have to calculate the Wronskian of v1 and v2. So the Wronskian is you take e to the x and e to the minus 2x, and their derivatives, e to the x and minus 2 e to the minus 2x. And when you calculate the determinant, you get minus 2 e to the minus 2x times e to the x, that's e to the minus x, times e to the x, e to the minus 2x, minus e to the minus x. So this is minus 3 e to the minus x. And the right-hand side of this equation, this is the r of x. So the particular solution will be something of the form y1 of x equals t1 v1 plus t2 of x, v2 of x. Right? These are the v1 and v2, e to the x and e to the minus 2x. What are t1 and t2? So t1 of x is the integral v minus v2 of x times r of x over w of x. So this is minus the integral. What is v2? E to the minus 2x. What is r of x? E to the x plus e to the 2x. What is w of x? Minus 3 e to the minus x dx. We have to do that integral. Minus times minus is plus a third. The integral of e to the minus x over e to the minus x is 1. And e to the minus 2x times e to the minus 2x is 1 over e to the minus x is just e to the x. So this is equal to 1/3 x plus e to the x. That's what t1 of x is equal to. 1/3 x plus e to the x. For better or worse, you actually have to do some work to solve the problems in this class. They're not all baby problems. What is t2 of x? t2 of x is the integral of v1 of x, r of x over w of x dx. What is v1? v1 is e to the x. What is r of x? E to the x plus e to the 2x. What is w of x? Minus 3 e to the minus x dx. So I can take the constant outside, minus a third, the integral of, here I have e to the 2x over e to the minus x is e to the 3x. Here I have e to the 3x over e to the minus x is e to the 4x. So this is equal to minus a third. The integral of e to the 3x is 1/3 e to the 3x. And the integral of e to the 4x is 1/4 e to the 4x. So that's what I got. Yeah. Minus 1/9 e to the 3x minus 1/12 e to the 4x. So this is t1 of x, and this is t2 of x. So a particular solution of this equation, y1 of x, it's t1 v1 plus t2 v2. So that's equal to this times v1 of x minus 1/9 e to the 3x minus 1/12 e to the 4x times v1 of x, which is e to the x, plus, oops, sorry, this is t1 of x. t1 of x is, all right, so this is t2, and v2 is e to the minus 2x, plus t1, 1/3 x plus e to the x, times t2, times, t1 is 1/3 x plus e to the x times V1, which is e to the x. So it looks like I get minus 1/9 e to the x minus 1/12 e to the 2x plus 1/3 x e to the x plus 1/3 e to the 2x, and 1/3 minus 1/12 is 1/4. So this is minus 1/9 e to the x plus 1/4 e to the 2x minus 1/12, oops, sorry, plus 1/3 x e to the x. So that, which I believe is correct, is a particular solution to the differential equation. And the general solution would be this particular solution plus any linear combination of the solutions of the homogeneous equation, C1 e to the x plus C2 e to the minus 2x. So this is a particular solution of this differential equation. And this is the general solution. Yeah, pretty good. A lot of fun. Okay. All right. Let's keep going. So there are two special kinds of nonlinear equations that we are learning how to solve. The first I did last week, and that was separable equations. And let me just review one example of that. Let me just find the section in the text, and I will pick a problem. So this is special methods. I should say methods for special nonlinear first order ordinary differential equations. And the first example were separable. And separable equations means you can write its first order. So y prime is some function of x and y. And separable means you can actually separate the right-hand side into a product of a function of x and a function of y. And in that case, what you do is if r of y is different from 0, then you can write this as 1 over r of y, y prime equals q of x, or 1 over r of y dy dx equals q of x. And then the miraculous formula, which works even just by the brilliance of the notation, though it's justified just in terms of change of variables, the integral of 1 over r of y dy equals the integral of q of x dx. And from this equation, if you can do the integrals, you get some function of y equal to some function of x. There are no more derivatives. So you have what is at least an implicit solution of the ordinary differential equation. And let me just pick more or less at random one of the homework problems to do on this. Let me just take the first one. So, so I think the first problem that was assigned, I guess these are due tomorrow, but that's okay. Number 2. So so this is on page 347, number 2. We have the equation tangent x cosine y Actually, yeah, even though I didn't assign it, let me do number 1 first, because that's really straightforward and you just do it. So on page 347, number 1, the differential equation is y prime equals x cubed over y squared. So why is this separable? Because this is, you can think of this as y prime equals the function x cubed times the function 1 over y squared. So my q of x is equal to x cubed, and my r of y is 1 over y squared. All right, so this is only for y different from 0, because you can't divide by 0. And you bring the y factor from the right side to the left side. You get y squared y prime equals x cubed, or y squared dy dx equals x cubed, or y squared dy equals x cubed dx, as if this were a fraction. And then you put integral signs in, and you have this equation. This equation says 1/3 y cubed, that's the integral of y squared dy, is equal to the integral of x cubed dx, which is 1/4 x to the 4th plus a constant. Or if you don't like fractions, you could multiply through by 12. You would get 4y cubed equals 3x to the 4th plus 12 times a constant, which is just a constant. Or you can either just say, okay, so the solution y is defined implicitly by the equation 3x to the 4th minus 4y cubed equals a constant. Or you could actually, if you wanted to solve for y cubed is 3/4 x to the 4th plus a constant. So y is the cube root of 3/4 x to the 4th plus c for any constant.
Professor,
Yeah.
I couldn't find that page from the homework, the fifth homework. I just download the PDF file, and the final page is 339. So I don't see beyond that page.
Okay, so when
yeah.
class is over, I'll go back and I'll double check on the website. And if I don't find it there, I'll scan it and email out right away. So you'll have it within an hour or so after class ends. But I'll make sure you get it.
Thank you, appreciate it.
Now, sometimes these problems are a tiny bit trickier. Let me look at number 2 on page 347. Number 2 is the differential equation tangent x cosine y is minus y prime times the tangent of y. So this is certainly not in the right form to be separable. The right form is when y prime is a function of x times a function of y. So all you have to do, though, is divide through, basically solve this equation for y prime. So y prime is tangent x cosine y over minus the tangent of y. So this is minus tangent x times cosine y over tangent y. Now tangent is sine over cosine, so I can also write this as minus tangent x times cosine squared y over sine y. And now this is in separable form. Q of x is tangent x. R of y is cosine squared y over sine y. So if I divide by y, that's by r of y, if I bring this over to the other side, I get sine y over cosine squared y dy dx equals minus the tangent of x. And then I can integrate. Now, to integrate sine y over cosine y, if we let u equal cosine y, du would be minus sine y dy. So except for the minus sign, that's what we have. So this becomes minus the integral of du over u squared. And the integral of minus 1 over u squared is 1 over u. U minus 1, you differentiate, you get minus u to the minus 2, which is 1 over the cosine of y. And over here we have minus the integral tangent is sine x over cosine x, which you might remember, you should remember, is the logarithm of cosine, is plus the logarithm of the cosine of x. So what we get is that 1 over cosine y equals log of the cosine of x. I just want to check that I haven't lost a sign somewhere. Yeah, that looks good. So yeah, so you can leave, this is a solution, or if you like, you can exponentiate and you get that cosine x is equal to, plus a constant. So if you exponentiate, you get cosine of x is e to the 1 over cosine y times some other constant. And that's how you use separability to solve this differential equation. Okay. So the remaining special technique is a homogeneous differential equation. So this is homogeneous first order ordinary differential equations. So we say that a function of two variables, f of x, y, is homogeneous. I mean, there's a more general definition of homogeneous. So this is really homogeneous of order 0, but it doesn't matter, homogeneous. If for all x and y and all t not equal to 0, if you multiply x by t and y by t, that's the same as f of x times y. It's like the t's disappear. So a function that satisfies this functional equation is called homogeneous. So what's a simple example? Well, f of x, y equals x over y is homogeneous because f of tx, ty, that's tx over ty. T is non-zero, the t's cancel. This is x over y. That's f of xy. Or if you take the function f of xy equals 2x plus 3y over 7x minus 1y, I claim that's homogeneous. Why is that? Well, if you take f of tx ty, that's 2tx plus 3ty over 7tx minus ty. You factor a t out of the numerator, you get 2x plus 3y. You factor a t out of the denominator, you get 7x minus y. The t's cancel, and this is f of xy. So there are lots of examples of homogeneous functions. And a homogeneous differential equation is y prime equals f of xy, where f of xy is homogeneous. And there is a little, if you like, magic trick, which allows you to solve such a differential equation. So if x is any non-zero real number, then y prime, which is f of xy, you can think of this as x times y over x. So this is, here we have the same number x in the first coordinate and the second. So think of x is equal to t. You can cancel the x. This is f of 1 y over x. So if f is homogeneous, the equation y prime equals f of xy is the same as y prime. Any solution of this will also solve the equation y prime equals f of 1 y over x. And this suggests introducing a new variable. So suppose we let v be equal to y over x. And it turns out this little trick of introducing a new variable, v equal y over x, reduces this homogeneous equation to a linear equation, which we can then solve. So let me just do a couple of examples so you see in practice how this works. So the method is, when you have a homogeneous function f of xy, in the ordinary differential equation, y prime equals f of xy, substitute v equal y over x. In other words, v is y rather is xy. Sorry, if v is y over x, y is x times v. And y prime, by the product rule, is xv prime, x times the derivative of v plus the derivative of x, which is 1 times v. So let's look at an example and see how it works. We have y prime equals y minus x over y plus x. So this is homogeneous. And if I want, I can write this as x times y over x minus 1, x over y over x plus 1. The x's cancel. Y over x is v. So this is v minus 1 over v plus 1. Y prime, what is y prime? Equals xv prime plus v. So I have xv prime plus v is v minus 1 over v plus 1. So xv prime is v minus 1 over v plus 1 minus v, which is, if I put everything over a common denominator of v plus 1, that's v minus 1 minus v times v plus 1. This is v minus 1 minus v squared minus v. This is equal to minus v squared plus 1 over v plus 1. So we have x dv dx equals minus v squared plus 1 over v plus 1. If I rearrange this, this is separable. This is, if I bring the x over here, so this is a function of v times a function of x. If I bring this from the right side to the left side, I get minus, well, I get, let's say, v plus 1 over v squared plus 1 dv dx equals minus 1 over x. Okay, so let me just stop for a minute because there's a lot of writing and it's hard to follow, I'm sure. We start with a differential equation right here. So this is a first order differential equation. It is nonlinear, right? This is not linear. This is not, it's not linear. But it is homogeneous. This is a homogeneous function of x and y. You can see that right away. If you factor out the x from the numerator and denominator, I get y over x minus 1 and y over x plus 1. And then I introduce the new variable. I define a function v to be y over x. So this is simply v minus 1 over v plus 1. And y prime is xv prime plus v. So from this equation, when I introduce the new variable v, I get a differential equation in x and v. So now my unknown function is v, and it satisfies this equation. If I bring the v over from this side to this side, so I'm looking at xv prime as v minus 1 over v plus 1 minus v. And I subtract fractions. This is what I get. So I have this, which is separable. And when I separate it, I get this. And then I integrate. So the integral of minus 1 over x dx is the integral of v plus 1 over v squared plus 1 dv. Let me write this as two integrals. This is the integral of v over v squared plus 1 dv plus the integral of 1 over v squared plus 1 dv. This is 1/2 the log of v squared plus 1, and this is the arctangent of v equal to the integral of this, which is minus log x plus a constant. So what I have is 1/2 the log of v squared plus 1, or 1 plus v squared, plus the arctangent of v equals minus the log of x plus a constant. And v is equal to y over x. So I get 1/2 the log of 1 plus y squared over x squared plus arctangent of v, y over x, let me simplify this a little bit. This is 1/2 the log of x squared plus y squared over x squared plus arctangent of y over x. This is 1/2 the log of x squared plus y squared minus 1/2 the log of x squared plus arctangent of y over x. But the log of x squared is 2 times the log of x. So this is 1/2 log of x squared plus y squared minus just the log of x plus arctangent of y over x. And this is all equal to minus log x plus a constant. The log x's cancel. So we get 1/2 x squared plus y squared equal plus arctangent y over x equals a constant. So, oops, I forgot the log. So 1/2 log of x squared plus y squared plus arctangent y over x equals a constant. So this defines implicitly the solution of the differential equation. You can't solve this for y, but at least we have the relationship between x and y, and we've gotten rid of the derivative of y. So we consider this a solution of the differential equation, but it is an implicit solution.
Professor, what is homogeneous? Because the right hand side is not equal to 0.
No. So this is right. So this is using homogeneous in a different sense. So the word homogeneous is used, unfortunately, in 2 different ways in this part of ordinary differential equations. When we talk about a first order equation being homogeneous or a second linear, when we talk about a linear first or second order equation being homogeneous, we mean the right-hand side is equal to 0. When we're looking at these nonlinear ordinary differential equations, homogeneous means, let's see where I put it. Yeah, exactly this. We have a function of 2 variables. So we say a function of 2 variables, f of x, y, is homogeneous if it has this property that if you multiply x and y by the same number t, it doesn't change the value of the function. So f of tx comma ty is the same as f of x comma y. So this is the definition of a function of 2 variables being homogeneous. And a nonlinear equation is homogeneous in this sense. So it's a completely different, it's a different use of the word homogeneous. If it's of the form y prime equals f of x, y, where the right-hand side is a homogeneous function, not 0, but a homogeneous function. So I agree, when you first hear it, it can be confusing because you think of homogeneous as meaning a differential equation where the right-hand side equals 0. But in this case, the right-hand side is not 0. The right-hand side is a homogeneous nonlinear function of 2 variables.
Yeah, this is the reason, because a non-linear.
Right, but again,
is a non-linear type. I don't know.
Again, it's just the word, and the words aren't important. It's the concepts that are important. So let me do a couple of problems involving homogeneous equations, homogeneous in this sense. So let's see. So this is on page 350. Let me start with one of the homework problems. number 2, y equals minus x over y. So we can do this. I mean, this is already separable. Y prime equals minus x over y. So we could just say, so this using separability, y prime equals minus x. So y dy is minus x dx, and you integrate. So you get 1/2 y squared equals minus 1/2 x squared plus a constant, or if you multiply by 2 and rearrange this, x squared plus y squared equals c. So any solution of this equation satisfies this, is defined implicitly by this, which just means a circle. So y equal the square root plus or minus the square root of c minus x squared. But these are circles. Suppose we try to use the fact that the right-hand side, f of x, y equal minus x over y, is homogeneous. And the rule is let y, that v, equal y over x, or y equals xv. So y prime is v plus xv prime is minus x over y is minus 1 over v. So when you make this substitution, this is what you get. In other words, xv prime is minus 1 over v minus v. This is minus v squared plus 1 over v. Or when you rearrange it, v over v squared plus 1, v over v squared plus 1, v prime is minus 1 over x. If you write v prime as dv over dx, then you see immediately how the integral of v over v squared plus 1 dv is minus the integral of 1 over x dx. This is 1/2 times the log of v squared plus 1 equals minus log x plus a constant. So the log of v squared plus 1 is minus 2 log x plus a constant, or minus the log of x squared plus a constant, which means well, if you exponentiate, let's just say, v squared plus 1 is minus x squared yeah, I'd rather do it like this. So if you bring this over to this side, you get the log of v squared plus 1 plus the log of x squared is a constant. And this is the log of the sum of logs is the log of the product, x squared times v squared plus 1. So if you exponentiate, you get x squared times v squared plus 1 is e to the c, which is just some constant. And v is always equal to y over x. So this is x squared times y squared over x squared plus 1 equals a constant. When you multiply through, you get x squared plus y squared equals a constant. So when we solve the problem using the fact that this equation was separable, we got this solution. And when we solve the problem using the fact that this equation is homogeneous, we get the same solution. And it's a matter of choice which method you use, because no one cares about the method. They only care if you get the right answer. Any questions about this? I mean, every day there's a new technique. There's a lot to know. And this is all just background, because in this course, ordinary differential equations is not a prerequisite, but you can't solve a partial differential equation without knowing how to solve at least a few basic ordinary differential equations.
Professor, I learned another method that is called the reduction order applied to non-linear ordinary differentials.
I'm sorry, you learned another method which has what name?
The reduction of orders only apply for non-linear cases. Is related to the new technique you teach us?
Well, if this is a first order equation, how would you reduce the order?
I mean, I don't know, for the second order, it's not for the first.
Right, but now we're just looking here at first order equations. Right, nothing more complicated.
Okay, thanks.
Let's look at number 5. We have the differential equation 2y squared minus x squared y prime plus 3xy equals 0. So you would expect this is a separable equation because it's a problem on the section about solving separable equations. So you have to, first of all, put this in the form y prime is a function of x and y. So you would write 2y squared minus x squared y prime is minus 3xy. And then divide by this, y prime is minus 3xy over 2y squared minus x squared. So on the right-hand side, we have the equation f of xy equal to this. So we have to answer the question, is f of xy homogeneous? Well, to answer the question, you compute f of tx comma ty. So what is that? This is minus 3 tx times ty over 2 times ty squared minus tx squared. What is this? I have minus 3 tx times ty is t squared xy. And here in the denominator, I have 2t squared y squared and t squared x squared. If I factored out a t squared, I would get 2y squared minus x squared. And when I do that, I see in the numerator, I have a t squared. In the denominator, I have a t squared. They cancel. So I'm just left with exactly this. F of xy. So this equation is homogeneous. Is f of xy homogeneous? The answer is yes. So our method says let v equal y over x. Or we substitute v equals y equals xv, and y prime is x v prime plus v when you differentiate this with respect to x by the product rule. So what do we get? We get y prime x v prime plus v is minus 3 x times y. What is y? xv over 2 y squared, that's xv squared, minus x squared. What is all this? It simplifies. We get minus 3x squared v over, and in the denominator, I can factor out an x squared. I get 2v squared minus 1. And I see that the x squareds cancel. So this is just minus v over tv squared minus 1. So xv prime is minus v over 2v squared minus 1 minus v. See, this is minus v, if I factor that out, 1 over 2v squared minus 1 plus 1. And if I put that over a common denominator of 2v squared minus 1, this is 1 plus 2v squared minus 1, I get a 2v squared. So this is minus 2v cubed over 2v squared minus 1. So v prime is minus 1 over x times 2v cubed over 2v squared minus 1.
Professor.
And this equation,
Professor.
yeah. Is there a question?
Yes, xv prime equals minus 3v, the line before the last one.
Here?
Xv prime equals minus 3v, not v.
Oh, thank you. Thank you. So xv prime plus v is this. I forgot the 3. Thank you very much. So this is minus 3v over 2v squared minus 1. So if I factor out a minus v, this is 3 plus 1. So then this becomes minus v, 2v squared minus 1. I have 3 plus 2v squared minus 1. Is that right? So this is 2v squared minus 2. So 2v squared minus 2. Thank you. So this equation is separable. So now I have to try to solve it. So I get 2v squared minus 1 over 2v squared minus 2 dv dx equals minus 1 over x. So if I integrate and I bring the dx over there, I get that. Okay? Does that look all right? So then I have to figure out, how do we do this integral? Well, I notice that 2v squared minus 1 over 2v squared minus 2, this is the same as 2v squared minus 2 plus 1 over 2v squared minus 2, which is 1 plus 1 over 2 v squared minus 2, or 2 times v squared minus 1. So I think I have this identity. And of course, this is minus log x plus a constant. So now I'm afraid I have to turn the page over. So minus log absolute value of x plus a constant. Right? That's this, equals this integral, which is the integral of this. 1 plus 1 over 2 times v squared minus 1 dv. So that's the integral of 1 dv plus a half the integral of 1 over v squared minus 1 dv. And I can do this by partial fractions, I believe. So 1 over v squared minus 1 is 1 over v minus 1 times v plus 1. That's equal to 1 over v minus 1 minus 1 over v plus 1. So half of that equals half of that. Sorry, a half. So 1 over v squared minus 1. Let's see, let's just check this. This is v plus 1 minus v plus 1. That's 2. And cancel the 2. So this is correct, I believe. So this is equal to, this is just v plus 1/4 the integral of 1 over v minus 1 minus 1 over v plus 1, which is v plus 1/4 the log of v minus 1 over v plus 1. And v equals y over x. And if I plug that into this, I get v is y over x plus 1/4 times the log y over x minus 1, y over x plus 1. I get y minus x over y plus x when I substitute. So I don't guarantee that this is right. First, I should probably exponentiate and get rid of the logs and so forth. But this is the method, right? And you always have to double check and triple check and so on. So this is a technique to solve homogeneous equations. And if you haven't seen it before, it really is very useful to know this method. Any questions? Questions? All right. So that's exactly what I had wanted to cover today, homogeneous equations. And as soon as we log off in a minute or so, I'll double check the website. And if the homework problems aren't there, I will scan them and upload them right away. Okay. And we have class tomorrow. It's a condensed week. Oh, before we go, let me just, I always like to jot down attendance. Attendance doesn't count in your grade in any way, but I always like to know who's around. So I have Boazuni, there you are, and Cabrera, Milenko, Yapur, Jeremiah Lee, and someone whose name is Galaxy J6 Plus. If you tell me your name, I can.
This is me, Jose de Leon Taveras. I log in using my cell phone.
Yeah, that's okay.
Mm-hmm.
No, you're right, De Leon.
De Leon, right.
Yeah. Okay, very good. Thank you. All right. Same time, same place, but the usual Zoom login tomorrow.
Have a nice day, Professor.
Okay. Bye, everybody.
Bye. Take care.
Thank you.
Thank you. Bye.